So imagine the following situation. We're given some function, and let's call it f of t. And let's consider some constant a. And let's consider first taking the definite integral from t equals a to t equals x of this function f of t. Now let's first try and understand what this integral represents. So let me get a picture going. Here is t, here's the y-axis, and here is a sketch of just some wiggly function f. And here is the starting limit a. Now the integral of this function f of t, the definite integral, represents the net area under the function, from the lower limit of integration a to the upper limit of integration x. But imagine that right-hand limit x as being allowed to slide back and forth. It's being allowed to vary and be scooched either to the left or to the right. A question becomes, as we slide x to the left to the right, how does the net area under the graph of this function f, how does that net area change as we adjust and slide the value of x? And that's the question that we're asking when we take the derivative with respect to x of this integral. We are asking, what is the rate of change of net area as we adjust to the right-hand limit? Now, beautiful result. As it turns out, the rate of change of the net area of this function can be found just by plugging in x to the integrand. Let's try and understand what's happening here. If we look at this diagram, and we have the net area under the curve at some initial value, and then we scooch that x value just ever so slightly, a little bit to the right, then we have picked up a slice of area of height equal to the output of the value at that x value, roughly speaking. And so f of x is the height of the added slice that gets picked up as we slide the right limit x a little bit to the right. A bit to the right. Now, be careful as you're going to use this theorem to take the derivative of an integral. The first warning is that if you're going to apply this theorem to take the derivative of an integral, the lower limit of integration must be a constant. Must be a constant. It could be 0, 1, 3, but it absolutely cannot be a function of x. It must be a number. The upper limit of integration as well, we must be careful. The upper limit of integration must be x. It cannot be x squared. It cannot be x plus 7. It cannot be the square root of x. It cannot even be a number. It has to be x precisely to apply this theorem. Now, let's consider the following concrete example. Here, this exercise, find the derivative of the net area under the graph of e to the t squared, left limit 0, upper limit x. So let's find the derivative with respect to x of this area with a sliding right-hand limit. Now, the first thing that we need to do is check to make sure that this integral is in the correct format to apply the fundamental theorem. The lower limit, 0, is a constant, so that's checked. The upper limit is just x, so that requirement is also met. Therefore, the rate of change of this net area is equal to the output of the integrand at the upper limit x. So I can replace t in the integrand with the upper limit x to get the rate of change, And my final answer would be e to the x squared. So that's the idea of this theorem. To find the rate of change of an integral, first check if it fits into this precise format: lower limit number, upper limit x. To find the derivative with respect to x, replace the dummy variable in the integrand with that x variable.